Welcome to Chapter 2. Here's where we're going to introduce the concept of frequency distributions. How do we start to organize our data? What's the difference between a table and a graph? What are the different types of distributions of data that we can look at? All that and more coming up. This might be one of our shorter lectures because a lot of this stuff may seem conceptually very similar to things you've already covered, either in previous classes or seeing in reading articles or just being exposed to data. But note that we're going to start working on being more precise with terminology, especially with notation, some of which we're building off of what we learned from the last chapter. Also, it's important to consider that some of the things we'll cover in this chapter are from what I have covered in previous editions of Statistics in Psychology or Quantitative Methods textbooks. These may not overlap exactly with the OpenStax books. And again, the OpenStax books that we're using for this class aren't my first choice necessarily, but I do use them because they cover the essentials and it is the more affordable option for students. So keep in mind, some of the stuff we cover in here, this narrated slideshow, might not be in the book chapter, and also vice versa. There might be some things in the chapter that we don't cover here, but typically they'll balance out and they'll overlap eventually by the time we get to the first exam in this class. Quick rundown of what the plan is for today's lecture. So first of all, we're going to review some of the most important things we covered in Chapter 1. We will discover what a frequency distribution is, how they can differ from a table versus a graph. We'll look at distributions and talk in a larger sense about why they're important. And a hint, they're going to be very important for this class, distributions, understanding them, knowing what they look like, knowing what a more usable one is compared to a less usable one. We'll also talk about percentiles, percentile ranks, and also stem and leaf displays. So first off, let's look at our review of Chapter 1. What is the difference between a sample and a population? Well, first of all, what do we call a characteristic of a population? That is a population parameter. Second, what do we call a characteristic such as an average of a sample? And that is a sample statistic. So it's really important to know the difference between populations and samples and population parameters, where we know for sure all the characteristics of a population, whereas a sample, we just have the statistic for that sample, but we may, if we think that sample is representative, be able to infer things about the larger population that we might not know about. We might not know the exact parameters, but if we have a good sample, we can make good inferences about what the parameters might be. We can estimate. What is sampling error? Sampling error is just the difference between when we take a sample, how different are the statistics from the sample we get from the larger population. Keep in mind that, let's say I'm deciding whether to pay an NBA basketball player the max salary. Well, let's say I watch that player play 5 games and the player averages 35 points. Well, I think, well, the statistics look good for that sample, but that sample size of 5 games is a small one. So can I infer that that player's performance over 5 games is going to generalize to the larger population of all the games that that player might play over the lifetime of the contract, for example, 4 or 5 years? I would say 5 games is not a big enough sample size. A small sample such as 5 games has tons of sampling error. Maybe it's early in the season where teams are still getting used to playing. Maybe it's late in the season where some teams aren't trying as hard anymore and not playing their best players. Maybe this player is really healthy, but always gets injured midway through the season. So my sample of 5 games would not be a representative sample for the lifetime of 5 years of a contract if I wanted to give it to that player or offer it to that player. And that 5-game sample would have a lot of sampling error. What would I want? I'd want multiple seasons at least of playing most of the available games and averaging a lot of points or whatever statistic I'm looking for to judge player value. So again, sampling error is a hugely important concept for us to consider anytime we're dealing with a sample and want to make inferences about what we think the larger population parameters might look like. We're estimating from a sample. We know there's going to be some sampling error, but how much is there going to be? Sample size is part of it, but we'll discuss other factors moving forward. Related to that line of thinking, we have descriptive stats, which basically are the stats that we are just talking about our sample, and that's all we care to describe. We are just describing the sample we have. But if we want to infer about the larger population, then we're doing inferential statistics. So for example, going back to the basketball players' 5-game sample. If we just want to say, it looks like that player played really well on those 5 games, yep, we are describing that sample only. If we say that, well, we think that player played that well for those 5 games, we think he's going to play that same level throughout the rest of the season, that statement is making more of an inference about the larger population, and we moved into inferential statistics thinking. What are some methods to investigate relationships between variables? The big ones are correlations versus experiments for our purposes. If we have correlational data, we tend to use one set of tests, and if we have experimental data, we tend to use another set of tests. What is a variable? If you remember from the last narrated slideshow, it is anything in which people will differ on value. If they're all the same, it's a constant. But if it's different, for example, most of the things we care about, gender, socioeconomic status, educational background, income, height, weight, those are all variables because people in a given sample are likely to have lots of different levels or values of the variable. Independent variable, dependent variable, here's where we're talking about an experimental situation, and the IV is the thing that the researchers manipulated. It's not something you came into the study with, it's something that you're either assigned to the control or the experimental condition. And since we manipulate that, and if that causes a change in a dependent variable, the thing that comes after, we say that that dependent variable was dependent on what level of the IV you got. And then we can say the IV looks to have caused a change in the DV. Also important to always consider the scales of measurement. And if you remember, they kind of move up from little information to higher levels of information. So we can start with our discrete variables, which are first categorical. We just put them into different categories. No other real ordering that we can do. Then we can move to our other discrete variable, which is ordinal. And ordinal variables, we can put them in order, but the differences between those levels aren't equal. Then we can move to our 2 continuous variables. So we first have interval, where the intervals between measurements are equal. That allows us for more precision in using those numbers. And then finally ratio, scale of measurement, where there is an absolute 0. So it's very important to always think about what kind of variables you have, because that leads you into how to properly choose the statistical analysis. And then finally, what's the order of operations? If you remember the Please Excuse My Dear Aunt Sally or PEMDAS acronym. So we have parentheses, exponents, multiplication, division, and then addition and subtraction. And finally, what do the following symbols mean? First, we have our x and y variables. If we think about on a graph, our x is our flat or horizontal axis, our y is our vertical axis. More importantly, we can think about x and y in both the correlational or the experimental framework. In the correlational framework, we think about x as a predictor, something that comes first and predicts the outcome, something that the predictor predicts an outcome. If we think about an experiment, our x variable is usually our IV or independent variable. Our y variable is typically our dependent variable in an experiment. We also have big N, little n. Big N refers to a population size. Little n refers to a sample size. So it's always very important to consider, are we dealing with a sample or a population? And then finally we have our Greek letter sigma, which means add everything that follows it together. Let's start off with frequency distributions. When we have small amounts of data, we can use each potential value or each actual value. So you see we have a set of scores here of 7. Now if we have a sample or a population of 2,000, we don't want to put all those individual data points in a distribution, so we'll have to somehow organize it and shorten the number of values and lump some together. We can think about tables and graphs as describing, organizing, or representing data. And the basic goal is to summarize the distribution. So we want to know kind of what the average is and how much spread out around the average is, and where the outliers or the extreme values on either the high or the low end, where they fit. So moving forward, these are the types of distributions that we're going to look at for this class. So starting with the frequency distribution table, again, look at notation here. So we have X, which is our possible scores. It's a variable because we have a bunch of different potential X values. Then we have a frequency. So our italicized F, which is the frequency of that score. So for example 3, we see 15 people, let's say, had a value of X equals 3. We also have this Fx, which is the sum of all the X's. So we have frequency of 9 people that had an X value of 4. If we add those 9 X values of 4 together, 4 plus 4 plus 4, and so on, then we get to 36. Then we can also look at performing computations. So we're dealing with a big N, so we're dealing with a population size. And if we want to know the population size, we can just add up all our frequency values, because we know each person has a score that's in one of these. They each have an X value, and if we add all the people with all the people with an X value of 4, those 9 people, plus all the people with an X value of 3.5, those 10 people, and so on, that's essentially our sigma F, which we could just put at the bottom of this column. Sigma F equals the sum of all these F values, as you can see calculated here. Now let's see if we wanted to take all our X values and the total X that we have. We can see the formula for that. So we would take all of our Fx, the frequency of X, times that value, gives us our Fx, or our total X, for X equals 4. So let's say these are GPAs. We wanted to know if we added all the GPAs of 4 together, this is our total GPA. It's not an average yet, we're just adding them up. And you can see we take our Fx column and then sigma that, and then you can see our total X equals this value. There's some other things that we can do with this logic. So we can also look at the proportion or the percentage of scores in each category. So our proportion is of the total group, what proportion has a certain score or a certain range of scores. And we have a formula for that. Notice we're referring to P as a proportion. We'll also talk about later P as a probability, but here we're just talking about it as a proportion. And then we take our big N, population size total, okay? And same from, how do we get that? Our sigma F, which we know is going to be 60 from the last slide, and then our frequency of that X value. So for a more concrete example, we want to know the proportion of scores relative to the total scores that have a value of 3.0. And we see we plug in the values, our population size 60, and just that number of scores, or our frequency of scores of 3.0 of 15. and then we reduce that down and we get 0.25. So that's the proportion of scores receiving a 3. If we want to convert that into a percentage, all we do is then add this times 100. So we take this decimal, and a percentage is never a decimal, so it's just times 100, convert that into our percentage. And again, we need to work on being precise with what this is. 25% represents the percent of scores, X scores, of a value of 3 out of the total scores in this population. So it's a lot of different pieces to keep in mind at the same time to be able to be precise about what we're describing here. Now, the previous examples were with a smaller amount of numbers where it's easy just to put them all in one table and be able to represent each individual value. Now, what happens if we have a lot more scores and we have a much wider range of values? This is where we might want to use a group frequency table. So you can consider these raw scores here. And there's a wide range. So we see a low of 20, it looks like, and then maybe a high of all the way into the high 90s. So instead of having a row for each value, counting back 100, 99, 98, 97, let's just group them into groups of 10 or intervals of 10. So then we look, what's the frequency of values between 90 and 99? So then we add up any value between 90 and 99 to get our column value or frequency for that interval. And we've kind of done the work for us ahead of time, and you can see that we're taking this raw data up at the top, a lot of different values, not very organized at all, and now we put it into a grouped frequency format, and we can see that, yes, it's a lot more organized, a lot more easy to interpret. So once again, how many values out of this, let's call it a sample, we don't know if it's a sample or population, let's call it a sample. How many values are between 60 and 69? Boom, frequency of 7. 7 values out of all the values are between 60 and 69. We can also move from looking at individual scores and look at accumulation as we move up or down in values. So this describes particular scores relative to others in terms of a rank or a percentile rank. So percent of individuals with scores at or below a given value. So when a score is identified by the percentile rank, we call it a percentile. So if you scored in the 90th percentile, that means your score is equal to or higher than 90% of all the other scores. So if you're at a high percentile rank, you know that you are in the very upper level of the total sample. If you have a very low percentile rank, you know that you're lower than most of the values in the sample. And if you're in the middle, well, you're kind of in the middle around the 50 percentile. How do we calculate this? Here we introduce a new concept. Instead of just the frequency of a score, now we're looking at the cumulative frequency, taking all the scores that are at or below that value. And each time we move up a value, we add more scores that are at or below that value. So if we look at it in terms of a formula, we have what we can call a cumulative percentage. Take the cumulative frequency over our population size, and then since it's a percentage, times 100. So for example, we can organize this data in terms of look at the different potential X values we have and the frequency of each value. And with the cumulative frequency, we start at the very bottom. Our first interval is X of 1. We have 2 of those, so we have 2 that are X of 1. And then now the cumulative part, we're moving up to the next interval, which is x equals 2. We have 5 of those, so we add all the values of 1 and 2 together for a cumulative frequency of 7. Once we move up to 3, we have another person that we're going to add to this new cumulative interval. And then we see our very highest level, x of 5, should be our total sample size or population size, because we're dealing with a big N, because every score is a 5 or lower. There's no score higher than that, and the cumulative frequency represents that by showing that that is equal to our population size. We can also look into graph form, moving out of the table arena. So now we're looking at a picture. And here we already talked about the horizontal and vertical axes. Our horizontal axis is usually our x, our IV in an experiment, or our predictor in a correlational design, and the vertical is the y-axis, again, the dependent variable in an experiment, or the outcome in a correlational design. And we can look at individual or group data, just as we were doing with tables. So for example, if we have a frequency distribution of this range of values, so x of 1 to 6, and we see our frequencies here. Notice we aren't doing cumulative frequencies, we want to know how many for each value are in the sample. How frequent is the x value of 3? We see it has a frequency of 4 total values that are 3. And we see how each of these individual values corresponds to one of the bars in this, what we're going to call a histogram. And just a quick contrast, here we're doing individual scores. There is a bar for each individual score, but if there's a high number of potential values, a wide range of x values, you don't want to have a bar for, you don't want to have 100 different bars. So for example, if you have a lot higher range of values, then you can do your grouped frequency histogram or graph in this case. So each bar in this case represents a 2-unit interval instead of a 1-score interval. And I sort of previewed some of the distinction between this terminology in the last slide, but basically we can look at different types of distribution graphs. What we looked at before was a histogram on the last slide. This is where we have to consider what kind of data we have. This is for interval or ratio scales. And notice that you don't have to have an absolute 0 here. You could start, for example, with height. If someone's a person, they don't have a height of 0, so we consider that to be just an interval scale for practical purposes, although you could argue that yes, it's possible to have a 0 in height, but since nobody would, we would consider it an interval scale for that variable of height in people. The other thing to consider is that, you know, these intervals, the difference between 67 and 66 and 67 and 68, those intervals are exactly the same. The width of the bars is going to be exactly the same across the range of potential values, and that's when it's appropriate to use a histogram. And that's what visually what working with a interval or ratio level scale, continuous variables, looks like. We also have bar graphs. This is when we have, instead of continuous variables, we have one of the two discrete variables, either nominal or ordinal. So if it's personality type, there's no real order in terms of better or worse. We have an extrovert, an introvert, and an ambitious person. You just gotta, it doesn't matter which one gets listed first, right? And then we have the frequency of the different personality types. Now, if it was, going back to the fast food example of fries, it could be that we have small fries, medium fries, large fries. In that case, it would be an ordinal scale, and we want to put them in that order. But notice that the intervals, the difference between a small and a medium and large French fries aren't exactly the same, and we represent that in the graph by having a gap between the bar. So histograms, the bars touch, the intervals are equal. Bar graphs, there are no equal intervals, You may be able to order them, but the bars do not touch because this is discrete data. And then finally we have polygons, which instead of using bars like a histogram, we just have dots and then kind of connect the dots. But notice that the polygon and the histogram are both representing, they'll look exactly the same in terms of the raw data that you're using. The only difference is that do you want to use bars or do you want to use the lines? And that's really an aesthetic choice rather than a practically different choice. We also have what's known as a stem and leaf display. I won't spend too much time on these, but you'll see them once in a while. So an alternative way to look at data, ordered data, but you don't have to use a frequency table or a graph in this case. The one thing is that it's kind of nice because if you think about a bar graph from the last slide, or excuse me, a histogram from the last slide, you have those connected bars. First of all, you don't know the exact values, and you can look at the frequency, but if you group them, if a bar represents an interval, variable or values between 30 and 39, for example, if you're just looking at a frequency histogram, you might have 3 values between 30 and 39, but you don't know exactly what those values are. So the one advantage to the stem and leaf display is that it's using an interval, in this case, the interval of tens, which is every number in the total sample or population that starts with a 3 is in this row. And we see, in this case, we know the exact value of those 2 data points. So not just the frequency, 2 values in the 30s, but we know one is a 32 and one is a 33. So the advantage is that it's pretty easy to put together, and it identifies every score in the data. You know all the exact score values, which if you're using an interval histogram or polygon, you know how many within that range you have, but you don't know the exact values within that range. The last thing is that it also provides kind of a picture. So if we think of a distribution as normally flowing from low and then having a lot of average values to high, fewer extreme high values, you can kind of see that a stem and leaf is just flipped on the side like that. We see there's relatively fewer of these lower values and higher values and more of the in-between or intermediate kind of values. So it does give you a little raw sense of the actual shape of the distribution of the numbers in the sample or population. And then finally, you can easily split the data into more precise intervals. We also have frequency distribution graphs. And this is what we've covered so far is mostly thinking from a sample statistics standpoint. We're just looking for a way to organize in a more convenient or easy to digest way characteristics of our sample. But what if we're looking more toward thinking about populations? What if we want to take our sample and think inferentially about what the larger population might look like? Well, sometimes populations have a lot of data points in them, and so that can really complicate a histogram if you have thousands of data points potentially. And the question is, how do you graph frequencies of data that you don't have? Well, we're starting to do inferential statistics. We're going to have to do some estimation. And we deal with this specifically in 2 ways. So one is relative frequencies. So in this case, we have the absolute frequencies of our sample data. We have all the numbers in our sample that we want. But if we're trying to take the shape of our sample and guess about what the population might look like, we'll talk about maybe relative frequencies. And we'll come back to that and show that visually in a little bit. In this case, Unlike the polygon where we're connecting the dots and it might look a little uneven, the smooth curve kind of rounds out some of those chunky differences between the dots on a polygon or the bars on a histogram. And this is going to be what we're going to use more often, is generally what does the distribution for a population of scores look like? And that's the idea of relative frequencies. It's nice and smooth. And we're saying that we don't know the exact number of scores that are 85 of IQ in the entire US population, but we know there's going to be about this many at 85, this many at 90, this many at 100, right? We're saying that we at least have a good enough sample to know that it looks relatively normal, which normal distribution we'll talk about in a little bit and many more times. High in the middle, low on the tails, and that middle is exactly in the middle and not skewed to one side or the other. And again, the smooth curve shows that we're not saying this represents the exact frequency. We're saying that we have enough sample data and we trust enough that it's generally going to look like this, and this is close enough for us to move forward with. We don't need to know all the exact values in a population if we're confident that it looks close enough to this. Let's also think about the difference between discrete versus continuous measures. So we have a difference between the technical and conceptual interpretation of the data. So for example, if we're thinking about IQ, we typically think about IQ as one number, right? You have an IQ, if it's average exactly, we say it's 100, right? And then maybe if you're above average, you get 101. If you're below average a little bit, you get a 99. Notice that those are just numbers, right? The numbers are in some ways a little discrete. The test only gives you exact numbers, but conceptually, here we're thinking about more, I guess, hypothetical constructs. Something like IQ in reality should be measured in decimal points too. It's not just exactly 100. And so that's what the difference between the actual data we have, the numbers, are a little bit more discrete compared to how we think about it conceptually or at the construct level, right? And so that smooth curve also allows us to infer not just at the exact number values, exact intervals, but also the intervals within the intervals, the decimals to the 10th place, to the 100th place, to the 1000th place. So another example of just kind of working through what I was trying to describe is that we can only measure things so precise, even though at the construct they're infinitely precise at the construct level. So that's kind of theoretically the difference between moving from precise measurements, but it may be somewhat more limited intervals compared to what the actual construct is. And you can see that's represented roughly here versus the nice smooth thinking about how constructs really are at that sort of more abstract, if we could measure them perfectly, it might look more like this in the smooth normal curve. So finally, a couple more things to point out about distributions. A lot of times we don't care so much about the exact values in our theoretical population distribution, as we'll find out. We just want to know generally where's the middle and what's the range, how spread out around the middle are the scores, and what's the shape. And one of the big questions is it symmetrical and normal, or is it skewed or asymmetrical? So first of all, we have what's known as a symmetrical distribution. Again, high in the middle, and that peak is right in the exact middle for us, and you cut it in half at that peak, and you fold it over, and they line up perfectly. That's a symmetrical distribution, and it would be a mirror image if you cut it in the middle. Now, of course, sometimes we get data that's not symmetrical. It is skewed. So one thing to remember definitely is we have two different kinds of skew. one is a positive skew. And notice, positive skew, it seems like the higher peak is on the negative side. Well, what we're going to find out once we get to central tendency is that in a positive skew, the peak or the highest number of scores might be right here, but the average or the mean is going to be pulled in the positive direction. So the biggest number of scores or highest frequency is here, but the average of all the scores is here. And we'll find out later on in a symmetrical distribution, the highest frequency of scores at the peak and the average of all the scores is at the exact same place. Now the same logic applies to a negative skew, which is the highest frequency of values, or the peak, is on the positive side or the higher side of the distribution, but when the peak is on the higher side, that will pull the value, the average or the mean of all the scores in a negative direction from the peak of the highest frequency. So we'll talk about distributions throughout the semester. It's most important, though, to think about, what does your data look like? Is it skewed in any way? Because as we'll find out, there are a number of assumptions that are associated with any statistical test. And the more you deviate from those assumptions, the more it may not be appropriate to use a certain statistical test. So in almost all cases, what we hope for, what we're looking for, and what we have the most faith that our statistical analysis are trustworthy is when we have symmetrical data. So more on that to come, but I think I'm going to wrap things up here. Looking forward to hear what questions you have, or what relationships or connections you can make from concepts covered here to things that you've had to deal with or seen in your own life. So looking forward to continuing these discussions in the discussion boards.